Okay, so let's talk a little bit what we talked about yesterday. So I talked a little bit at the beginning of class of how to determine when a function is increasing or decreasing. I think what we came up with was a function is increasing anywhere where the derivative is positive, right? Because that's giving you a positive rate of change. And a function is decreasing wherever the derivative is negative. Okay, and then I also talked a little bit about finding what are called the partition numbers or critical numbers, which tell you possibly where a function is going to change from increasing to decreasing. It's a place where the derivative might change sign. Okay, so first of all, a partition number is just a number where the derivative is 0 or undefined. A critical number is just a partition number that's also in the domain of the function. Okay, and we'll talk a little bit more about what's special about critical numbers as opposed to partition numbers. So I think I started with an example. We wanted to find critical numbers and find the intervals of increase and decrease of this function f of x, which is x squared times the square root of x plus 1. Just for reference, I wrote down the domain of this function. The domain is -1 to infinity. That comes from the fact that you need x plus 1 to be greater than or equal to 0, meaning x would have to be greater than or equal to -1. Okay, notice, right, you can plug -1 in and get 0. It's okay to take the square root of 0. If you tried to plug anything less than -1 into this, like -2, you'd be trying to take the square root of a negative number. So I took a derivative using the product rule, and we went through the algebra and simplified our derivative, and I got x times, in parentheses, 5/2 x plus 2, and in the denominator I got x plus 1 to the 1/2. Okay. Now, algebraically what you would do is, if you want to figure out where, especially if a derivative is a quotient, if you want to figure out where a derivative is 0, you set the numerator equal to 0. Okay, so what I did was, I don't think I did this in class, but I set the numerator equal to 0, which would tell you either x is equal to 0 or the 5/2 x plus 2 is equal to 0. Okay, so that gives me the first partition number of 0. Okay, that's a place where the derivative was 0 or undefined. And then if you solve this second equation for x, you can subtract 2 and then divide both sides by 5/2. That's where the -4/5 came from. And then the denominator is going to equal 0 and x equals -1. Okay, so those are the partition numbers. And then what makes a partition number a critical number we talked about yesterday? If a partition number is also in the domain, it would be a critical number. So you might notice that all three of these numbers are in the interval from -1 to infinity. Okay, so these partition numbers are also what we call critical numbers. Okay, now for the sake of finding intervals of increase and decrease, what you do is you can make a number line if you like, and you can put all your partition numbers on the number line. Okay, and then we'll talk more about critical numbers in the next section, what's special about them. Okay, it turns out if something is a critical number and the derivative changes from, say, increasing to decreasing, then you have a local maximum at that critical number. Okay, but for actually finding intervals of increase and decrease, you just find the partition numbers. Again, you find your derivative, you figure out where it's 0 or undefined. I got these three values. I put them on a number line, and that splits up the domain from -1 to infinity into 1, 2, 3 intervals. Okay, and on those intervals, the function has to be strictly increasing or strictly decreasing. Okay, so my first interval is from -1 to -4/5. Since this is -1 and that's actually -0.8, I picked the test value right in the middle, -0.9. From -4/5 to 0, I just noticed that -1/2 or -0.5 is something in that interval. And then the last interval from 0 to infinity, I just picked my test value to be 1. Now what you're going to do is you're going to plug all your test values into the derivative, and you're going to note what the sign is. So let's see. I guess I can get out the calculator here, unless someone's already done these.
I did it.
Oh, okay. So when you plug -0.9 in, now you're plugging that into the derivative.
Yeah.
And did you get a positive or a negative number?
Plus.
Okay, so you plug that in the derivative, you get a plus. And then what about the next one?
A negative.
Okay, you get a negative for the negative 0.5, and then my guess, does it change to a plus at positive 1 again?
Yeah.
Okay, so you plug 1 into the, I think that's pretty clear, right? Plugging 1 here is positive, 5/2 times 1 plus 2 is positive, and then the square root of 1 plus 1 would be positive in the bottom as well. So sometimes you can just look at it and figure out what the sign is, but if you're not sure, plug your test value into the function, you can use a calculator. Now, you don't really need the table. You're going to see this on your homework a bunch of times. Some of you might have already looked, but on this interval, the derivative is positive, so you put a bunch of plus signs. On this side, the derivative between negative 4/5 and 0, the sign of the derivative was negative. And then as soon as you get past 0, the derivative is always going to be positive again. Okay? And then what that tells me is that f is, anywhere the derivative is positive, f is increasing. So f is increasing on the intervals -1 to -4/5. And the other interval would be 0 to infinity. Okay. And then you can say f is decreasing. There's only one interval left. That's this interval -4/5 to 0. Okay. And what I'm going to do, let me just, since I don't want to mess with turning the projector on, I am going to just draw a sketch of the graph for everybody real quick, just so you can see what it looks like. So I'm going to go to Desmos. I'm going to try and go to Desmos. Internet's not working anyways. Oh, come on. Don't do this to me. Maybe the guest works. Okay. What are the plans this weekend? Got a lot of homework? Work? Where do you work, Missy?
Harbor Freight.
Harbor Freight? Oh, cool. It's like over by Albertsons and all that stuff. Selling tools, all that kind of thing.
Yeah. Quality tools.
Is it pretty reasonably? I guess I don't really know how much tools cost in general, so.
They're cheap.
They're cheap over there? Like inexpensive cheap or like crappy cheap? Both? Yeah.
She's a worker, she's an employee, she's like, I gotta say, that's confidential.
Yeah, I'll go over there and tell them what you said.
It's okay, I'm leaving in a month anyway. So.
Alright. Okay, so Desmos isn't working, which kind of frustrates me a little bit. So I think for now I'll just have to maybe scrap the drawing a graph part of this. But you can always verify your answer. Just go into Desmos, enter the function, and you'll be able to verify that the intervals that you found were correct. Although on the test you won't have Desmos, so. And then once we build all of this stuff, section 4.2 is using second derivatives to know if it's curling up or down on a particular interval. We'll be able to draw some pretty good sketches of these graphs by hand. And you'll see they look pretty close to the actual ones when we use technology. So my guess is the internet will eventually start. Has anybody noticed it's been pretty poor today, or how's it been? Have you worked in the tutor lab yet?
Yeah, a couple people had trouble,
Okay.
like even emailing. So.
Okay, so it's not just me.
Yeah.
Okay. So moving on then. So like I said, once I get technology working, we'll actually graph some of these things to verify our answers. Okay. So now what we're going to talk about is how to use this idea of critical numbers, finding intervals of increase and decrease to find what are called the local maximums and local minimums. Now, I will give everybody a little bit of preview. Since -4/5 and 0, those were in the domain, they're critical numbers. This is the place where the derivative changed from positive to negative. So kind of what's happening here, I'll just kind of draw a rough sketch. I guess -4/5 is over here. right? You know, this might be the point on the graph. To the left of that point, the function's going up, and to the right of that point, the function's decreasing. Okay? So anytime you have a critical number and the derivative changes from positive to negative, the function was increasing, you hit a maximum, and then it started decreasing. Now, just like at 0, you know, maybe the value of the function at 0 is down here. Your function would be decreasing to the left of 0, but once you get past 0, the function's going to change to increasing, so maybe you'd have something that looks like that, a local minimum. Okay? Now, on top of page 3, I'm defining what the local extrema are, which is just all the relative or local max and mins. I guess I could talk about this definition. Maybe I'll write it down. So, definition, let I be the domain of F. Okay. We're going to say f of c, so an output value or a y-coordinate on the graph. And anybody have a guess as to why I use c? C usually represents our critical numbers. Okay, so that's why they chose c. So this is what we call a relative min. I'm going to abbreviate. If there is an open interval I, 1, within I, containing C, so that f of c is less than f of x for all x in I. I'm only going to write down the first one because the second definition is the same thing. It's just that it's a relative max, so the inequality is flipped around. But, so like here, in my graph up here, 0, well, here's the origin. So f of 0, I guess that's what this is. That's f of 0, the height of that point. That's a relative minimum because I can find a little interval surrounding c, and then that would just give me one little piece of the graph. So maybe on this little tiny interval now, I look at that little piece of the graph, and on this little piece of the graph, f of 0 is less than all the other f of x's. Okay? So that's why we call them relative or local minimums. It's like if you could zoom in far enough, meaning ignore the rest of the parts of the graph, maybe I just look at this piece right here, then on just that little piece, that function value is a minimum. Just like over here, I can zoom in far enough, I can ignore the rest of the graph, and then f of negative 4/5 is less than all the other function values. Okay, so that's all this definition is really saying. It's saying you can zoom into the graph far enough so that it looks like a maximum or a minimum. Okay, so you can read through the formal definitions if you want to, but I think just kind of understanding the idea is probably more important. So, right, and if the graph like went down forever, right, that's not the minimum value of the entire function. That's just a minimum if you zoom in and look at that little teeny piece. So that's the idea of a relative or local max and min. And then the third definition, if you ever see this, you'll see something like a question will say find the local extrema. That just means find all the local maximums and local minimums. And like I said, there's something about finding critical numbers and where the derivative changes sign. That tells you where your local maxims and minimums are. So if I give you this function right here, we'll just find them real quick, just so we understand the definition. So I'm going to have to draw this by hand. Example 5. So here's my function. It looks like if I go 1 unit to the left, one of those little maximums is right there. And if I go 1, 2, 3 to the right, and I go down 5 units, you've got a point down here, and I think roughly the graph kind of looks something like this. Is that close enough? Mm-hmm. Okay. So I'll write this down here. This is the point minus 1, 3. Right here, this is the point 3, negative 5. Okay. And the question says find the local extrema. So it's saying what is the relative maximum value and what is the relative minimum value. So notice this function doesn't have what we call an absolute max or min, and we'll talk about those later when we do optimization. Okay, there's no maximum value on the entire graph because it's going up forever. So there's no maximum function value, and just like over here, it's going down forever. So there's no global or absolute minimum. But if you zoom in far enough, right, if we ignore the rest of the graph, we can find a little small interval so that the y-coordinate of that point on that little piece is a maximum. Okay, so what I can say here is 3 is a relative maximum. So it's the y-coordinate that's the maximum. Okay. You can also say where it occurs. So what x-coordinate does that little relative maximum occur at? Yeah, so that it happens at x equals -1, but the y-coordinate is what we call the relative maximum. You're kind of just looking for peaks and valleys, right? You're looking for the humps. Okay. And then what would be the relative minimum value? Is there a low point or a low hump somewhere?
-5.
Yeah, and the y-coordinate's there, it is -5. You could say -5 is a relative minimum. And if you like, you can say where that is achieved or where it happens. I guess we could say here that that relative minimum of -5 occurs at what x-coordinate? +3. Okay. Right. So when you're looking for relative max and mins, you're just looking for peaks and valleys. That's how I like to think of it. Okay. And again, they're not, that's why we say relative. Other textbooks use the term local max and min. Because if we just look locally or relatively and ignore the rest of the graph, we can look at looking at just this little piece, 3 is a maximum on that little piece. Or if I ignore the rest of the graph, I focus on a small interval, on this little piece of the graph, -5 is a minimum value. Okay? So that's where the term relative or local comes from. Okay? Now, theorem 2 is going to give us some insight. We're not going to prove this theorem. But local extrema are connected to critical numbers. So it turns out if f of c is a local extremum, then that number c had to be a critical number. Okay. And why is that? Because if you have a relative max, what's the slope of the tangent line at that point? 0, right? And critical numbers are numbers in the domain where the derivative is 0 or undefined. Right? Just like over here, if you have a relative minimum, 3 would be a critical number because the derivative at 3 is 0. Okay? So basically what this says is, this theorem is going to say that the only place where you're going to get local maxes and local mins are at the critical numbers possibly. Okay? So let's do one, and then I think I have it summarized. Well, all this information is going to give us a theorem or procedure. So you find all the critical numbers. So if you're reading this procedure at the top of the next page, on page 4, it says if you have a critical number, so c is a critical number, meaning f of c is defined and the derivative is 0 or undefined. Okay, so that's just saying the critical number has to be in the domain, and it's a number that makes the derivative either 0 or undefined. And then what you do is, just like in our previous example, you would make a little sign chart. You'd make your interval, you'd label your critical numbers. In the first case, at that critical number c, the derivative is changing in sign from negative to positive, meaning the function was decreasing and then went back up to increasing. In that case, f of c is a local minimum. Okay, so at a critical number, if the derivative changes from negative to positive, that's going to tell you have a local minimum at c. In the second box, if the derivative changes from positive to negative at c, then you have a local max there. And then the next two cases are, sometimes you'll have a critical number where the derivative doesn't change sign as you cross c. So it'll be positive to the left and right of c. So that means that f of c is neither a max or min, and the same would be true if the derivative was always negative as you pass through c. Okay, so let's kind of use that idea here. This is again called the first derivative test, and it helps you find local maximums and minimums. Example 6. So we'll just do this with a polynomial. We can do this with more complicated functions. I think you'll have to do some of that on the homework. So if I take f of x to be x cubed, yeah, Desmos still hasn't even opened yet. I could take x cubed minus 9x squared plus 24x minus 10. So this is a third degree polynomial. Okay. So A, we're going to find the critical numbers. So first you find what are called the partition numbers, and of those, whichever ones are in the domain are going to be the critical numbers. Now, what is the domain of a polynomial?
All real.
Okay, that'll just be all real numbers. So in this case, anything that's a partition number is automatically a critical number. Okay, so what do we do to find critical numbers? We have to take basically it's a calc class, right? If you're going to do anything, you have to take a derivative. So without even knowing what to do, it's always a good idea to take a derivative. So the x cubed, I think, becomes a 3x squared, right?
Mm-hmm.
And then minus 9x squared becomes
18x.
minus 18x when the 2 comes out front. The derivative of 24x is just 24, and the derivative of the constant negative 10 is 0. And like I said, this is where some of the algebra is going to come back into play. Because after you find your derivative, you're going to have to simplify it and do a bunch of factoring. Okay, so there will be some problems that are algebra heavy. Okay. And then now we can simplify this. Is there any constant that's is there a constant factor that's in every term?
3.
Yeah, I think you can pull out the 3 and have x squared minus 6x plus, would it be 8? 8 times 3 gives you 24.
Yeah.
And then if I did this right, I chose it in such a way that this would factor. Okay. So I'll take, otherwise what you'd have to do is set this equal to 0, and you'd have to use the quadratic formula on this if it doesn't factor. And then what's it going to factor as? You're going to have two terms that begin with x, and then I need to multiply to positive 8, and the two numbers need to add to minus 6.
Minus 2 minus 4.
I think minus 2 minus 4 will work. Okay. So, what we know is f prime of x will equal 0 or be undefined. So we just set that equal to 0. So is there anywhere where the derivative is undefined in this case? No, the derivative again is a polynomial, it's a quadratic. So no critical numbers or partition numbers come from the derivative being undefined. Okay, so, but when is the derivative going to be 0? When x equals 4 and 2. So let me write 2 and 4. Okay. Which are the critical numbers? Okay, so they're partition numbers. They make the derivative 0 or undefined. But since those numbers are also in our domain, they become critical numbers. Okay, so we got the critical numbers. That was part A, right? So now we need to find the local maxima and minima. So with the first derivative test, you always have to make a sign chart. So we're going to draw a little number line. I probably will skip the table this time. So for part B, make a number line. You can put your critical numbers on there. This is supposed to represent the x-axis, by the way, when I draw this number line. Okay. So I put down my two critical numbers. And how many intervals does that split up our domain into? 3, right? The stuff left of 2, the stuff between 2 and 4, and the stuff greater than 4. Okay. And then now you have to pick test values and plug them into the derivative. So what's a good test value over here? Something less than 2 that's pretty simple would be 0, right? How about a test value in the middle?
3.
We'll use x equals 3, and then why not just use x equals 5 over here? Now, when you get good at this, especially when something's in factored form like this, you could probably figure out the sign of the derivative without using a calculator. Because if you plug in 0, for x, 3 is positive, 0 minus 2 is negative, and 0 minus 4 is negative. So really what you're getting at x equals 0 is you get a positive times a negative, but two negatives make a positive, so the derivative is going to be positive to the left of 2. If you're not sure, just plug in 0 into your derivative and see what you get. I guess, actually, isn't it easier to look up here this time? Because if you plug in 0, these terms become 0 and you're left with 24, and that's positive. Okay. Here's a little trick also. Some of you might remember talking about multiplicities of roots. Okay, and a function will change sign if a multiplicity is odd. If a multiplicity of a root is even, a function won't change sign. So it might be beneficial to look this up, but because when the derivative factored has a single factor of x minus 2 and a single factor of x minus 4, the roots 2 and 4 are said to have multiplicity 1, which is an odd number, meaning that the sign of the derivative is going to change once you cross each root. But if you don't remember that fact or know how to exploit it, just pick a test value. If you plug 3 into the x plus 2 term, you get a positive. If you plug 3 into this, you get a negative. Positive, positive, negative is going to make the derivative negative. And then if you plug something like 5, that's the test value in the last interval, 5 minus 4 is positive, 5 minus 2 is positive, times another positive. You would get all positive values. So there's the sign chart. And then look at the derivative test. So look at your first critical number. I think this is like the second box on your first derivative test. So add a critical number. If the derivative changes from positive to negative, you can almost think of it like this. You know, the function is rising, 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 but at positive 2, what's going to happen? Now it's going to change to decreasing. Okay. So what does that mean? There's a local, let me use the notation in the textbook. There's a relative max at x equals 2 of, and then let's find the maximum value itself.
10.
Yeah, and where did you plug that into?
The original.
Be careful, right? Because now we're using the derivative to find the maximums of the original function. Okay, so once I know a local max occurs at 2, the max itself is going to be f of 2, which you said was 10, Nate?
Yeah.
Okay. And like I said, where I got that from, 2 cubed is 8, minus 9 times 4, 8 minus 36 is negative 28. Negative 28 plus 48 is 20. 20 minus 10 is 10. Okay, but you can always get out your calculator. So the maximum, the relative max occurs at 2, but the maximum value itself is the value of the function there, which would be 10. Okay. And then what about at 4? So what's happening here, right, is the function's decreasing, decreasing until I get to 4. And then because the derivative changes to positive, now the function's going to be increasing. So at x equals 4, we have a relative minimum this time. So I can just say it this way too. F of 4 equals, now has anybody plugged 4 into this yet?
6.
You get 6. So f of 4 equals 6 is a relative minimum. The function notation tells you the minimum value and where it happens, right? So 6 is the relative minimum. It happened at the x value of 4. Okay. So again, you can only have relative max or mins at critical numbers. Okay. And at a critical number, if the derivative changes from positive to negative, you get a relative max. If at a critical number the derivative changes from negative to positive, you get a relative minimum. And then now what we can do So we can go ahead, I think part C says to sketch a graph, right?
Yep.
Okay. So notice the function starts off increasing until at positive 2 you hit a local max or a relative max of 10. Then the function starts to decrease until you get to x equals 4. In that case, 6 is your relative minimum, and then after that it's just going to increase forever. So if I draw a graph, so this is part C, and for most functions it's harder to know the shape, but we have the added benefit of we kind of know a little bit about what polynomials look like. So let's see, when we're at x equals 2, so 1, 2, let me make some room. Make this a little higher. I'll go up 2, 4, 6, 8, 10. So I went up by 2's on the y-axis. So when x is 2, the output is 10, so you get a point there. And then I'll go 1, 2 units to the right till I get to 4. And I know I have a relative minimum at 4 of 6. And then, what would the y-intercept be?
It's negative 10.
Yeah, if you plug in 0, you get negative 10. So what I'm going to do is extend it downward. I'm just adding an extra piece of information so that my graph looks a little more accurate. So that'd be your y-intercept down there. When you plug 0 into the function, you get minus 10. And then, sorry, when I draw this, I like to kind of just do what happens at the local max and mins first. Right? Since that's a relative maximum, the derivative was increasing and changes to decreasing. That's a relative minimum. The function changes from decreasing to increasing. So that's generally what the shape of the graph is going to look like with my scaling that I chose. And like I said, we'll be able to take more complicated functions and know what their general shapes are once we have second derivatives. Okay. And then, anybody have any questions so far? Everyone doing okay? Alright. General ideas, pretty straightforward, I think. I think the hard part is doing all the algebra when you have to take the derivative and simplify and find where the derivative is 0 or undefined. Okay, so we can do an economics application here. Is it okay if I erase what's on the left half here? Are we okay? Okay, so example 7. Take a cost function for this is the cost of producing X hockey jerseys. Where the production level is strictly between 0 and 400. Okay. Now it's probably been a while since we've done this. Part A wants the average cost function. Okay, where did I just put that? There it is. Okay, so what's the average cost function?
Just the function over x.
Yep. So if you want the average cost of something, you take the total cost and you divide by the number of units produced, and that'll tell you on average, if you produce X units, how much does each unit cost to produce on average. Okay, so we'll do C bar of X is going to be the total cost function divided by the number of units. And again, that gives you the average cost per unit when X units are produced. And I'm just dividing every single one of these terms by X. So let's just actually go through it real carefully. Now, the way you simplify something kind of it matters what you're going to do with it. So we're going to be finding the critical numbers of this function, the intervals on which average cost per jersey is decreasing, and the intervals on which the average cost is increasing, and then find the local extrema. Okay, so I think what we can do, we can leave it as it is and use quotient rule, or we could, I guess, divide x into every term. So I think what I'm going to do is just use the quotient rule. Okay. Probably gives me a nice form for when I'm trying to find where the derivative is 0 or undefined. So again, if I want to find the critical numbers of this function, we need to take the derivative and find out where the derivative is 0 or undefined. So now we're going to do, where's the best place to do this? I guess I have enough room here. So quotient rule. The derivative will again be a quotient. And you always start in the numerator with the bottom function. So we'll do x times the derivative of the top function, which is 10 minus 0.4x. So bottom times derivative of the top minus the top function and then times the derivative of the bottom, but the derivative of the bottom is just 1. And then we'll divide that whole thing by the bottom squared. And now we get to do a bunch of simplifying. I don't think this one will be too bad. Could be worse. I think we just have to multiply the x through the first two terms, distribute the negative, and then add and collect all the like terms. Okay, we okay so far?
Do you have to distribute that x, or can you just assume that one of the critical numbers is going to be 0?
Well,
and then can you set
I don't think one of the critical numbers is going to be 0, because if I plug in 0 for x, that'll just go away. And plugging in 0 for those x's is going to leave me with minus 1500. Also, we can't even plug in 0 because of the bottom. Actually, so 0 will be a critical number, but it's just a critical number in the denominator. Okay. So let me simplify this now. C bar prime of x. You're going to get 10x minus 0.4x squared. And then you distribute the negative, you'll get minus 1500 minus 10x, and then plus a 0.2x squared. So I distributed the x into the first factor, and then I distributed the negative into the second factor, or the second term. And then you get a little bit of cancellation. I think the 10x's go away, right? And then the minus 0.4x squared plus the 0.2x squared. I believe we just get a minus 0.2x squared minus 1500 over x squared. So again, unfortunately in this section, always a good idea to simplify derivatives. Missy, you got a question? See it? Okay. Everybody okay so far? Okay.
Is the critical number going to fall in the domain?
So the numerator is going to have two roots, right? Because it's a quadratic. Yeah, one of them won't be in the domain, so that won't be a critical. So one of the partition numbers won't be a critical number. Okay, so let's go ahead and do this. So now C bar prime of x equals 0 when negative 0.2x squared minus 1500 equals 0. So again, if your derivative is a quotient, finding out where it's 0 is setting the numerator equal to 0, and where it's undefined is when the bottom equals 0. Okay. Although, when I look here, something bad kind of happens when we try and solve this.
You can't do anything with the negative.
Yeah, watch what happens when we try to solve for x. Well, you can add the 1500 and divide by negative 0.2.
Does the negative critical number become positive because of that negative?
Well, actually, what's going to happen here is to solve for x, you'd have to take a square root on both sides. But a
Right.
square root of a negative number is undefined as a real number. Okay. So what this implies is x is, I guess, a complex number. We don't study those, so there's no critical numbers where the derivative equals 0. So you set the numerator equal to 0 and try and solve, and you end up trying to take a square root of a negative number. Okay. Now, one thing I want to say, well, let me wait till we get there. So interestingly, there's no critical numbers where the derivative is 0. There's one critical number where the derivative is undefined. Anybody know what that one's going to be?
0.
Yeah. So if you look at the denominator, the derivative of the average cost function is undefined when x equals 0. Right? This quotient is undefined when the denominator equals 0, which happens when x equals 0. Okay. So what that means, this implies x equals 0 is the only critical number. Okay. So we got to think about what this means. So first of all, if I want everybody to maybe go back to the definition of local extrema, relative maximum, relative minimum. C has to be strictly on the interior of a domain. Okay, to have a relative max or min. Okay, so basically you can't have relative max or mins at endpoints. And since 0 is a critical number, and remember what our domain was? Our production levels between 0 and 400. Okay, so relative max and mins can only happen on the interior of a domain. So my critical number would have to be greater than 0 or less than 400 to be able to even have a relative max and min. Okay, so what I can conclude here is that since x equals 0 is the only critical number and is an endpoint of the domain, there are no relative extrema. Okay, there's no relative max, there's no relative min. Does that make sense, right? If you're on the endpoint, there's no room for the derivative to change sign once you pass that critical number. Right? I'd have to be able to, be in the negative direction a little bit and cross through 0 and have the derivative change signs. But if your critical number's on the endpoint, right, there's nothing happening to the left of 0. Okay. But we can still answer the question, because doesn't it say to find the intervals on which average cost is increasing or decreasing? It's one of the questions. You read it. Okay, so I answered the last question first. There's no local extrema because our critical number is an endpoint. Okay. But we can determine if I guess what that's just telling me is that the derivative has to have the same sign on the whole interval. Okay. So the derivative is always going to be positive or negative. Anybody have a guess? The bottom's always positive. X squared's always positive. So if I take a negative number minus a negative number, that derivative is always going to be negative. You can take a test value if you want, plug in positive 1. If you plug in positive 1, you get minus 0.2 minus 1500, which is negative, divided by 1, which is positive. Okay, so what I'm going to say here, let me write it up here. Sorry, I'm kind of all over the place, but so since c bar prime of x is less than 0 on this interval from 0 to 400, that's our domain, the average cost is decreasing, or I'll just say is always decreasing. And I guess it does say find the intervals of increase and decrease. So i.e. c bar prime of x is decreasing. Now what interval am I going to say it's decreasing on? So it's always decreasing, so over the entire domain. So it'll be 0 to 400. Question is, do you use brackets or parentheses? Anybody have a guess?
Brackets, since you included.
Yeah, I actually agree with the parentheses, folks. Whenever you're saying something, whenever you're giving intervals of increase and decrease, it's always on the open intervals. So you always use parentheses. Okay. So it's increasing on its entire domain, but when I talk about decreasing on an interval, we don't include the 0 or 400. Now, in the last minute here, let's think about what this means. So what would that mean if your average cost is always decreasing? So let's think in the business economics terms. What would that mean if we were always increasing the production level? The average cost per unit will always be decreasing, meaning the more and more units we produce, right, your cost per unit is also going to be decreasing. Okay? It means you're just basically getting a better deal the more units you produce. So again, that just means if your average cost is always decreasing, it just means that the more and more units you produce, the average cost per unit would be going down. So you'd be paying less per unit the more and more units you produce. Okay. So this was kind of a weird example where it's kind of a trick question, right? What are the local extrema? Oh, there are none because the only critical number was an endpoint. And then since the only critical number was an endpoint, that means the function is always increasing or always decreasing. And just by either looking at it or plugging in a test value like positive 1, we see that the average cost function is, the derivative is always less than 0, so the average cost is always decreasing. Alright, so we'll call it a day. Thanks everybody. I'll get the video for class posted. Exams will be graded by Monday. I'll try and get them done sooner, maybe on Sunday. We'll see what I can do. On Monday, we're going to start section 4.2, which is talking about concavity. Okay, so we're going to actually look at the second derivative, which is the derivative of the first derivative. So a little bit more tedious and cumbersome in the work. Is anybody going to be mad at me if I don't assign written homework? No? Okay, do me one favor though, just make sure when you're practicing this stuff, make sure you're methodical about it. Make sure you're drawing your number line and you're making your sign charts. You make sure you're getting the practice by hand. Okay?
You're talking about written homework for local one?
Yeah, there's no written homework. I'm just saying when you're doing the online, make sure you're being really good about doing your work on the side.
Is the online due Monday for 4.1?
No, if it is due Monday, I'll switch it to Tuesday.
Okay.
I'm not sure what it is. But, and if I forget to change it, just remind me.
Have a good weekend.
Yeah, you too.
See you, Chris.
Yep, see you later. Have a good weekend.
See you.
Does that mean demand is always increasing?
We're not talking about demand though.